Okay, good afternoon, everybody. Welcome to geometry. All right, we've got some fantastic stuff lined up for today. We're still studying triangles because there's just so many good things about triangles. They're pretty much the best shape. So we've got a couple sweet new properties to take a look at for those today. And they all have to do with inequalities. Triangle inequalities. That is to say, the triangle is not equal. You could go triangle equalities, but that would just be an equilateral triangle, and it'd be a much shorter, much shorter lesson. It's not as much. Actually, there's a lot of things you can do with that. I'm getting sidetracked. Anyways, so we've got two major properties that come out of this. The first is the triangle inequality, and then second is like subsidiary an inequality within a triangle. So let's start with the big one first. The by-name triangle inequality has to do with whether or not you can make a triangle in the first place. Okay? So roll your mind back to last week, the Pythagorean theorem. Okay? The Pythagorean theorem typically gets used for solving for the third side of a right triangle, given the other two sides. That's use number one. But we also said use number two, you could work it backwards and use that given three sides, prove whether or not it was a right triangle. Right? Whether if it fits into the Pythagorean theorem equation, then it is a right triangle, and if it doesn't, then it wasn't. Right? So you could make that as a test of right triangleness. We want to broaden that a little bit. Not just right triangles, but is there a test to say whether or not we can have any triangle at all? Okay? So imagine, if you will, you're out in the woods. Maybe this is like a survival scenario, and you've got to build a shelter to make it through the night. And you know, of course, that triangles are the best, sturdiest structural shapes. You're like, okay, I'm going to gather some sticks to build my triangle hut for the night. Can I get just any three sticks? Well, any three at all. Any ones that I grab, they will always be able to make a triangle out of. Yeah, it'd be like really scalene, perhaps. But can you make any triangle out of any three sticks? Or is there actually a limit? Is there some scenario where I could have three sticks that don't form a complete triangle? That is the question. So let's pretend these are the three sticks you have found. Well, of these five, let's pick a subset of these three. Let's start with the three colors. How about that? So question one. Three different colors. So take the green one, the red one, and a blue one. You can use either the short one or the long one. Doesn't matter. Manipulate them around in your mind. Tell me whether or not you could actually make a triangle out of those. I'm serious. I actually wanted to tell me. Go ahead in chat or out loud. What's your vote? Yes or no?
Like all of them together?
No, just three. So three colors. So we'll go with like these three for this test, and then we'll try different combinations. So start there.
All right.
And these three different ones form a complete triangle. And this is not just like a hypothetical survival situation. Engineers have to deal with this kind of thing all the time when building stuff. Like everything is built out of triangles, almost. Right? Lots of stuff, because it's such a stable shape. And so if you have a given parameter of, hey, we need it to span, this distance, so this side is set, and we only have so much material, so we can only make the other side this long. There's limitations here. Can we get a workable triangle within those parameters? That comes up quite a lot. We should address this. What's the limits? Fatima says no. These three cannot possibly form a triangle. we have any other votes? Ooh, Mariah says yes. And he says no. And he says, yeah, it's going back and forth. Yes, no, yes, no. Okay, looks like the no's are winning here. Let's see. All right, so let me get rid of my annotation here. I'm going to try to build these guys. So all I'm allowed to do is I can move these and I can rotate them. Okay, I'm not going to change the length here. Let's see if I can put this together. So tip to tip there, and then we got to grab this guy. If I spin him around, ooh, that's close. Ooh, I bet. Let's see if I stretch it out this way. The green one, maybe if I tilt it back a little bit. And then we brought the green one up here. Go back down a little bit more. What do you think now? Are we getting closer? Well, I think I've almost got it. Oh, too far. Trying to snap them together for me. Software, you're being a little too helpful right now. I want just a little bit. Oh. I think you get the idea. If it would let me fiddle with it, it's trying to snap things into place automatically for me, which I don't want. But I think we could see that I could mess with this a little bit more. I won't waste more of your time getting the details, but those are going to come together, right? Can we all agree on that now? That yes, this is definitely possible with these three. Okay. And how about with, going to be a lot of undos. Let me get them back into place. How about with the long one? Let's see if that will also fit into place. So for that one, I'm going to need this down here. See if I can attach these together. You go there, and then grab the red one. Maybe like that, just about, and then a little bit more fiddling, I could get it perfect, right? Is that convincing enough? I think I've about done it. Anyone not convinced? No? Okay, yeah. So with these three different colors, yes, we can. Next question, though, what about the three blue ones?
Obviously, can't do it with those.
Obviously, Jenny says. Why is it obvious, Jenny?
Because if the long blue one is on the bottom and then the two little ones are on the sides, it won't be able to connect at all because they're not long enough.
Yeah, these guys are too short. If I stick these on, let me tilt it a little bit so it doesn't go right on top. Yeah, if I match those to the ends of the long one, these guys, look at all that space in there. They're not going to meet together, right? They're too short. Yeah, clearly. So yes, I agree with you, Jenny. That's almost obvious there. So if you try to do all blue here, we're going to get, that's a no-go. Right? So there's definitely limitations here. We can't just pick any three lengths at all, right? Because you might end up with this situation where, however you want to phrase it, either those two of them are too short or the long one is too long, right? Depends on which direction you're looking at it from. Because those aren't going to meet up. And in fact, we could make an even more specific set. Let me make one. Let's say one like, say that, or let me get a thicker line here so you can actually show up. like that, and a purple one like that. Right, so those are now exactly the length of the blue line. Okay? So it's not that they're too short or too long. They're actually the perfect length to lie right on top of each other and make only another line of equal length. So that's not even good enough to make a triangle, right? If they fall flat into the middle, if you were lay the blue one down as your base and try to put the orange and the purple on top and have them like fall together and meet at the middle, they would just collapse. They would still fall flat, right up against each other, but still fall flat. You need a little bit more length in total so it can pop out and make that triangle. So I would phrase it this way. Here's the rule. If you want to build a triangle, no side may be equal to or greater than the sum of the other two sides. Right? And that's what we said. This blue one was too long, or it could be perfectly the wrong length, and any longer, of course, would eliminate it. So, and you have to check every combination, right? I can't overcompensate and say, oh, I need this guy to be longer, and you just make it longer, 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 longer. Well, now this one is longer than the sum of the other two, right? So they all have to be balanced in that way. If we were to name our sides A, B, and C, then you'd have to say, well, A cannot be greater than or equal to B plus C, and B cannot be greater than or equal to A plus C, and C cannot be greater than or equal to B plus A. Right? All of those have to be true. Now, in practice, do you need to test every combination? Usually not. Most of the time, there's going to be one of them that is the longest side, and you can just compare, okay, how about the other two compared to that? And you only have to do the one test, and you can be pretty confident that the rest of them will fall into place. But if they're really close to each other, I'm talking like extremes. Like you can like check in your head, okay? If I give you two sides that are both single digits, a 7 and an 8 inch, and then there's a 40 inch length, it's like, okay, yeah, no way. 7 and 8 aren't going to make 40, right? So if you can really quickly check one combination, be like, yeah, that fails at any one of these tests, it's already failed. You don't need to check all three combinations to fail it, right? It does have to pass all three for it to pass as a viable triangle. And that is what you'll be doing in exercises 1, 2, and 3 today. Okay, checking whether it's possible to draw such a triangle with the measurements. And when it's not, it asks make a sketch demonstrating why it's not possible. Draw something like this, like these are the blue guys here. Right, this could be your sketch. And then you would, of course, label these, be like, this is the 14 centimeter, this is the 40 centimeter, right? And you would show how they don't match up. Okay? Any questions on the triangle inequality? No? All right. Then let's look at the next related property, and that is the sub-inequalities within a given triangle. And that has to do with who is smallest and who is the biggest. Okay? This is somewhat intuitive, I would say, for some of this. Take a look at this triangle ABC down here, and I'm going to adjust the lengths of some of these things to make it even more extreme here. Okay? I can make this really skinny triangle. Okay? Which side is quite clearly the biggest?
A.
A, right? So why don't I rank down sides biggest to smallest? Would you definitely say A is bigger than B and B is bigger than C? We can agree on that?
Yes.
Yeah. And I know I didn't move my labels around, but I think you can follow those. Now, it turns out that there is a direct correspondence between the lengths of the sides and the measure of the opposite angles. So angle A here is across from side A. It's the longest side, and we can conclude quite safely that it must be the largest angle as well. So angle A will be greater than angle B, and it'll be greater than angle C. And certainly by the time we get to C, we can tell teeny tiny side, teeny tiny angle, right? Even when I move things around. Okay, so as long as side A is the longest side, angle A will always be the biggest angle, right? Anyone not convinced of that? What happens if I do this? Which one's the biggest angle now?
B.
Now it's B. Which one's the biggest side?
Both of them.
Well, both of them are the. You can't have two biggest.
They look like the same length.
Which ones? This is side A. This is side B. This is side C. Which one looks the biggest?
B.
B still looks the biggest, right? Yeah, I realize I happen to make A and C look kind of similar. That still holds. We'll get to that in a moment. But B is definitely the biggest side, and angle B, remember this is still vertex B. I can't drag the label along with the point. I would need to go to GeoGebra for that. But yeah, it's still across from the biggest. The biggest is still across from the biggest, and the smallest would still be across from the smallest. Although we can't quite tell which one it is. Let's write a new equation here then. Let's go with what we do know. We know B is the biggest, and it's greater than, why don't we set it up as such? Let's mark it. Hey, this is an isosceles triangle. A and C are equal length. That's okay. That's going to tell us that angle B is the biggest, and it's greater than angle A, which is equal to angle C. It still holds up, right? We can still transfer the relative sizes of sides to the relative sizes of angles, even when one of them is equal. Right? Oh, Fatima was just asking that. Yeah, exactly. Can the sides be equal? Totally. This is what you end up with. And even better, this also works in the other direction. This is a biconditional. If I know the relative arrangement, biggest to smallest, of sides, I can conclude the relative arrangement of angles. Also, if instead I know the relative arrangement of angles, I can then conclude the relative arrangement of sides. Isn't that neat? Like it's something that visually even small kids will pick up on. This is the smallest over here, and this is the smallest there. But putting it all together to say this is always across from the other, they will always go in the same ranked order, is pretty something. Not every shape can just do that, right? Triangles are special that way. All right. Any other questions then on that phenomena? No? Okay. Then another look at your exercises today. So 4 through 6, we'll make use of that. You're looking for, okay, where's the biggest? Here I have the sides. I need to know the angles. I don't know their measurements specifically, but I do know compared to 13 and 18, 20 is definitely the longest side, which means across from it, B has to be the biggest angle, right? I at least know that much. And you can go from there. Okay? And then 7, 8, 9, combine it with some other information. These are some interesting little investigations there, putting your knowledge together. Number 10, I would probably call the challenge question of the page. Okay? Why does triangle PQS, this one right here, have to be isosceles? Okay? So make use of that statement I made down there. To be isosceles, well, this guy looks to be the longest side. It's probably PS and QS that have to be equal to each other. I don't know anything about the side lengths. Oh, but what do I know about the angles? See if you can reason why the angles have to be congruent and force it to be isosceles. This is a great question to really bring together knowledge bits from across the Porter as we've done so far. Okay? And then 11 and 12, go ahead and cross those out. You can skip those. Those have to deal with compass and straight edge construction, which we are not dealing with this quarter. So just skip those last two entirely. All right. Final call for questions on what we're doing today. Set. Okay. Then one last reminder. I posted a video yesterday with some very important information about the end of the semester. If you haven't watched that yet, you need to watch that ASAP. Very good stuff about what all is coming up and when and how the points total together to create your grade and what you can do to improve your grade. All that information is out there. It's a nice short, I think, 8-minute video. Okay, very worth your time. Give that a watch. Otherwise, I will leave you guys with the rest of the class period to work. We've got 23 or so minutes. You could probably finish most of this page, at least like 1 through 8, probably. 9 and 10 are the longest. At least get through 8 done. All right? Let me know if you have any other questions as you work.